Oh, okay. I mean, first of all, thank you so much for the very nice invitation. I actually just said it before. Actually, I would have loved to come to Aachen in person, although it's difficult at the moment, obviously. But Aachen is actually one of my favorite cities in Germany. So I really, really like the city. Maybe we can do this at some other point.
Absolutely.
But thank you so much.
Sehr gerne.
Okay. Okay, I will come back to that. No, and thank you so much for the invitation. It's quite a pleasure. It's a huge pleasure to speak here. And if I can persuade more people to switch on their camera, I'll be very happy to, because it's always easier to speak when you see people. But of course you don't have to. Okay, but now I will just start speaking about stochastic gradient descent. And we see how that goes. Okay, so the title of my talk was just said is stochastic gradient descent in continuous time, discrete and continuous data. This is joint work with my friends here, Kessin Jin, Shengguang Liu, and Carola Schönlieb. So actually, Kessin and Shengguang are also in the chat. So if you have questions for them, just ask. And there's sort of like 3 papers that actually it's more like 2 papers. I just added a third one because you use similar techniques, and I will come back to that towards the end. Yeah, so this paper is not quite as relevant for this talk, but the first 2 are. Yeah, so this one, which appeared last year at some point in Statistics and Computing, is discrete data case, and the somewhat newer preprint up here that you can find in the archive is the continuous data case. And what I mean exactly by continuous data, I will explain throughout the talk, but we'll actually start with the discrete data case and sort of go slowly from there and speak about what does it actually mean to do stochastic gradient descent in continuous time, and why would we actually do that. Then sort of introduce this whole process and actually analyze it. Yeah, before then, and I try to keep this first like sort of half short, which usually doesn't really work, but we'll try to keep it short to then have more time to speak about the continuous data case. Just one question for the organizer. How much time do I actually have? It's like 45 minutes?
Yeah, you have 1 hour essentially. So just relax and okay. we keep the flow. Okay, we do it in continuous time, don't worry.
Okay. Okay, thank you so much. Okay, so let's start with the first problem setup, the discrete data case. So what we try to do throughout this first half of the talk is we try to optimize some function phi bar. And phi bar is given as this finite mean or sample mean of some other functions phi I. Okay, and these phi I say they're like somewhat smooth, and yeah, we probably need a bit more than this, but say for now it's like C1, and this thing actually has a minimizer. Okay, so it's a well-defined optimization problem, and of course problems of this form you can find in machine learning, you can find in statistics, yeah, where this could be like a maximum likelihood estimate, where these the sum over n is like sum over data. In machine learning, these could be loss functions. Yeah, in imaging, these could be like single pixels. You could sum over the pixels, for instance, of an image, and so on. Yeah, I mean, there's many different ways to interpret this kind of problem. But it's really, I mean, you can find it everywhere, essentially. The question is how to resolve a problem like this. So the classical strategy would be the gradient descent algorithm, actually going back to Cauchy, where we just say, okay, we have it's like an iterative method, and we have this following update rule. So we have theta k is given as theta k minus 1 minus some value eta k multiplied by the gradient of phi bar, and of course this gradient is given as just as this finite mean of the other gradients. Yeah, so that's very simple. And if this phi bar is like somewhat well behaved, so for instance, say it's like strictly convex, and this step size eta k is sufficiently small, then we can actually show convergence of this algorithm. The problem in practice is we somehow need to evaluate this gradient, which means we actually need to evaluate n gradients. And of course, in practice, this n could be 10 million or something like this, or 10 to the 15. And then we would need to evaluate 10 to the 15 gradients, and we don't have time for that. So what we do instead, and actually going back to this method by Robbins and Monroe, 1951, is we don't optimize with respect to this phi bar, the gradient of phi bar, but we actually just pick one of these terms in the sum at a time, and we choose randomly which term of those we take. Okay, and so we just like pick randomly sort of the loss function that we optimize with respect to, and we do one step optimization step with respect to this random loss function, and then we replace it by another loss function after this step. And here we need like some, for classical convergence analysis, we need some more assumptions there. So we need, usually it's like that the phi 1 through phi n are strongly convex. And this eta k, which is now usually called learning rate rather than step size, come back to that in a couple of minutes. It needs to go to 0 actually. Yeah, so just being small is not sufficient. It needs to go to 0, and it needs to go to 0 slowly. Yeah, whatever that means. Yeah, it means, I think, okay, it's an L2 but not L1 or something like this. Okay, so when I first encountered stochastic gradient descent, or maybe not when I first encountered it, but when I rediscovered it for me as an interesting topic, I thought, okay, what we get here actually is a Markov chain. Okay, so what is constructed by this algorithm is a Markov chain. We have this update rule. We do random update every step, and every step only depends on the last parameter. And what I was wondering is whether we can say certain things about this Markov chain. Yeah, so for instance, does it have a stationary measure? Yeah, and if so, is that like interesting? Yeah, I think some people say the stationary measure is something like a Bayesian posterior. Yeah, you can find work like this. Then there's like something called implicit regularization, which is also very much connected to actually doing stochastic gradient descent, not for an eta k that goes to 0, but for one that is probably constant, or one that is not going to 0, but to a fixed value. Then, I mean, if we have a stationary measure, do we converge to it? If we converge to it, is that fast? Yeah, which I think are very interesting questions. And why I think those are interesting is because, I mean, they might help us to actually get more efficient stochastic optimization algorithms. Yeah, so if we understand these properties, they actually allow us to understand random subsampling also beyond stochastic gradient descent. Yeah, so for instance, currently I'm looking in a project at doing subsampling in the filtering setting, where you have like a state space model and you don't observe all the signal at the time, which is like a similar question. And then, of course, one other goal of stochastic gradient descent usually is to use in non-convex optimization, where it's more robust than classical gradient descent, but hardly understood. And again, I mentioned this already. What actually happens when we leave this eta k constant, not let it go to 0, because that's by far the more popular way to do it in practice. When optimizing, like say, like when training a deep neural network, for instance, or something like this. Now I said we do it in continuous time. I think the main reason for me why I do it in continuous time is because I think it's a bit easier. Because I mean, usually when you do things in discrete time, or also here when we do this thing about this in discrete time, I mean, it's essentially it's a numerical discretization of something. Yeah, and I also try to understand it like this. And whenever I have a discretization of something, there's like particular points where I need to be like particularly careful, like things like stiffness, for instance. Yeah, so one problem of stochastic gradient descent could be that we use a forward order discretization of something that's very stiff, for instance. Yeah, but that's not very interesting for us when we just want to understand the subsampling. Maybe the stiffness is not actually something we should like care too much about right now. At some point we need to. Yeah, and therefore I kind of try to prevent looking at numerical artifacts or numerical problems by doing it in continuous time. The other reason could be, and I said this before for the filtering example, there's actually many methods, especially also in modern data science, that are formulated in continuous time. And so if we try to combine this with a subsampling, for instance, then it's quite useful to understand subsampling in continuous time as well. Yeah. I think those are my main reasons, actually. So how do we do stochastic gradient descent in continuous time? I think that's the main question. And I think the usual model for stochastic gradient descent in continuous time is a diffusion process. So what we say in this case is we let the eta k go to 0. Yeah, say we let all of them go to 0 at the same time. Yeah, so not over k, but like just uniformly. And then we can actually show, or actually I think it was shown in this work, Slee et al. 2019 JMLR, that this sequence converges to a certain diffusion process. It's like it's like a hard diffusion process, I'd say, because we have multiplicative noise here. Yeah, so it's not a simple diffusion process, but it's a diffusion process. Now, I want to go actually beyond this diffusion process because I think there's like two problems with it. While this model is correct asymptotically, yeah, it's a correct thing to do asymptotically as eta k is small. We're actually very often not very interested in the situation where eta k is very small. Yeah, because especially if we talk about like non-convex problems, for instance, this diffusion process will not tell us a lot, yeah, because there actually it's probably quite important to actually have a large eta k. And if eta k is large, stochastic gradient descent will be very much not a diffusion process, but it will be more like something, yeah, that varies much slower or varies much smoother actually, and has like certain kinks or something like this. Okay, so this will be quite different from a diffusion process. The other reason is when we look at this process and we say, okay, we want to create a new like a new algorithm from the continuous dynamical system. That's actually quite hard to do here because this dynamical system depends on phi bar. And but what we actually want to do is we want to subsampling. Yeah, so we want to have only one data set at a time, one gradient at a time, rather than having all of them at once here again. Okay, so actually this diffusion process doesn't actually give us any subsampling. Yeah, it just gives us a noisy gradient flow, which is interesting, but it's sort of hard to say, okay, we are given this this stochastic differential equation, and we now build a new algorithm that does some actual subsampling rather than like adding certain noise. Okay, but how do we do this? And that's sort of, I think, the first main part. So there's two observations, and one I sort of told you before. So if we look at this update from stochastic gradient descent, and it's exactly the same thing we've seen before, this is some Ford-Euler discretization of a certain gradient flow. And this gradient flow is this one. Okay, so we have just like the time derivative of theta is equal to minus this gradient of this randomly chosen phi ik. Now, if we look at the eta k, we have like two different meanings, two different properties of this that this eta k has. To some extent, it's a step size of this Ford-Euler discretization. Yeah, so it's like what we usually call like h or like maybe dt or maybe delta. Yeah, so this is just a step size in a Ford-Euler discretization. On the other hand, the eta k determines how long we wait between two data switches. So that means, I mean, this eta k gives us a certain length of an interval, and that's the interval with which we stick to this data set or this potential phi ik. Yeah, because once the step is over, we will sample another ik, and we have with a new data set. Okay, and we replace this data set by another data set. Okay, so this actually tells us, okay, so how long do we wait until we replace our current data set by another data set? And the idea is now to get a continuous time model for stochastic gradient descent by actually letting this step size go to 0. Yeah, so we really replace this part by this part, but we still switch sort of slowly between the ik. Okay, so we don't let these like switches between the data sets like become white noise essentially, or become white noise. But we switch the potentials still at a certain rate, and the rate is 1 over eta k. I will show you a plot in a minute that makes everything a bit clearer, but we need some more mathematical tools now, because now we have like a weird like discrete continuous setting in which this is a continuous dynamic, but ik is pretty much discrete. And we kind of need to connect all of this. And the idea is to actually use a continuous Markov process to replace this discrete ik by a continuous ik. And so what this does is just, I mean, if you've seen like a certain Poisson process before, this is just a generalization of a Poisson process, essentially, where we are on this index set. Yeah, so that's a set of all of the potentials, essentially. And this continuous Markov process just sort of jumps between those potentials, sort of back and forth. And it does so, I mean, after a random waiting time. Okay, and I mean, and in case of a Poisson process, this waiting time will always be exponentially distributed. In this case, it may or may not be. Yeah, we'll come to that on the next slide. But that's essentially the idea. Yeah, so we have this continuous process, and we choose which of the phi I k, or which of the phi I is taken at a certain time. We choose that using this continuous Markov process. So now actually I mentioned before that we're interested in the setting of a constant learning rate, and we're also interested in the setting of a decreasing learning rate. So the constant learning rate is probably the one that is more popular in practice, yeah, where we say, okay, we just leave it constant and we hope for the best, or we will hopefully get close to the minimizer anyways. Although we will probably not converge to a minimizer, but we will sort of like still wiggle around, but we will be close to the minimizer, hopefully. While in a decreasing learning rate case, we actually have a chance to converge to the minimizer as well, yeah, and actually stay there. So this is now fairly technical. What is important is we have two different processes. One is called I, one is called J. And the process I represents a constant learning rate. That just means that this waiting time distribution, yeah, so the distribution of these times in which we stay in a certain state, with a certain data set, say, that these are constant in time and they will be exponentially distributed. And in the second case, we actually have waiting times that get like sort of smaller over time, yeah, whatever that means. It's a bit hard to quantify, but I mean what it sort of means is when we choose the transition rate matrix, we let the entries go to infinity, essentially over time, yeah, of the transition, or minus infinity on the diagonal, plus infinity on the off-diagonal entries. Yeah, that's sort of the idea. Okay, and then we can define what we call stochastic gradient process, which has a constant learning rate in case we use I, and so I was the one where the waiting time distribution does not depend on time, or decreasing learning rate case where we use J, where the waiting time got smaller over time. And here's a plot I promised. So that's like how you can imagine this. We have this process I of t that picks certain data sets, and then we have the process theta of t that actually then optimizes with respect to those data sets. And so these are all just like very simple gradient flows that are like sort of stuck together. Yeah. So why do we use such a kind of a model? So these models are so-called piecewise deterministic Markov processes, and they are fairly well understood. Yeah, which is one reason for me to take one of these models, because it's they're much easier to analyze. Although they don't, I mean, so the random waiting times, for instance, you don't have those in practice, obviously. So that is a bit different to the original algorithm. Yeah, it makes the analysis much easier. That's one reason. The other reason is, or how I actually encountered them first, was in non-reversible MCMC algorithms. I'm sure there are some people in the audience who are very much aware of them. yeah, like the zigzag methods or the bouncy particle filter. Yeah, so all of these also use these PDMPs. Okay, so this like sort of is like a modeling work. Yeah, so we kind of need to compare stochastic gradient descent with the stochastic gradient process, and these first four are like fairly simple, I think. Yeah, so if we say, okay, what does stochastic gradient descent do? What does stochastic gradient process do? Yeah, so in both cases we have a gradient flow that is randomly, yeah, so random switching in a certain sense. Just in stochastic gradient descent, this will be a discrete gradient flow. In the stochastic gradient process, this will be a continuous gradient flow. So then we have uniform sampling. Yeah, so we sample uniform from this IK, or from the set of the potentials. I didn't quite explain this for the stochastic gradient process, but indeed we choose the index processes like I of t. We choose it in a way that gives us uniform samples in every step, or at least converges to distribution, to the uniform distribution. Then in both cases we have the Markov property. Then we have a certain learning rate, which sort of is the rate at which we replace one data set by another, and these learning rates actually they actually match. Yeah, so we can choose them such that they're very close corresponding to each other. Just the rate in the stochastic gradient process is like a bit of a different rate because the probabilistic rate. Yeah, but it's like a very basic idea, I think, from yeah, continuous Markov process, actually, what the interpretation of this rate is. And finally, and I think that's actually the most fascinating part, is approximation of the deterministic gradient flow, and I will say a bit more about this. So the idea is, or like maybe one reason, or like the philosophical reason behind stochastic gradient descent, which is a stochastic approximation technique. Yeah, so that's how Robbins-Monroe called it. It approximates something, and okay, we can discuss what it actually approximates, but I might say that what we actually do is we try to approximate this like sort of optimal gradient flow, yeah, where we look at the gradient of phi bar, yeah, the sort of one that we cannot really access. And stochastic gradient descent actually approximates this one. Yeah, so if we let the learning rate get very, very small, then okay, we have convergence of the Euler scheme, and we have like something like a law of large numbers or so that actually allows us to recover this gradient flow. And the question is whether the stochastic gradient process also approximates the gradient flow. And that's indeed something we could show. Yeah, so if we are in the constant learning rate setting and we let eta go to 0, then we can actually see that, okay, if the initial values match, we can actually see that the stochastic gradient process converges weakly to this full gradient flow. Okay, so with our technique, actually, we get a certain, it's a bit like a splitting technique, actually, that allows us to recover this full gradient flow in total if we let eta get very small. From a theoretical perspective, that's actually quite hard. I think showing things like this is actually quite hard. We used here this perturbed test function theory by Kushner, 1984, that looks at such, yeah, say like stochastic to deterministic limits of differential equations. We can also see this, so it's like very small experiment where this green line is the gradient flow we want to converge to, and then these other lines are stochastic gradient processes with different constant learning rates, and they get smaller. Yeah, so we have very large one, the blue is very large, and you see it's very, very noisy. Or they're all noisy, but it's like you have this like very, very smooth, long, and very few switches. But if you look very closely, so the one that is violet is very, very close, bounded to the green line. Okay, so we showed that our stochastic gradient process can approximate the gradient flow, the actual gradient flow, and we also see it numerically, which I think is very nice. Okay, but I promised at the beginning to say something about long-term behavior, so we should do this as well now. So the question is, what actually happens to these processes theta, that was constant learning rates, and xi, if time is very large? Yeah, so do they maybe converge to stationary measures? If they converge, how fast do they converge? And especially for the decreasing learning rate case, for xi, can we actually show that we converge to the minimizer? Yeah, because that's like still the original problem, is like actually want to optimize something. And therefore we need to know whether we actually have a chance of converging there. So we measure convergence in a certain Wasserstein distance. Yeah, so that's probably by now pretty much standard. The only weird thing is sort of we use this like bounded Wasserstein distance. Yeah, so normally you would only have like some LP norm here, but we actually bound it by 1 as well, which is useful because we actually have, okay, we have like, so this Wasserstein distance is equivalent to B convergence. Yeah, so if we see convergence in here, we know it converges weakly as well, or if and only if it converges weakly as well, and we don't have to worry about certain moments. Yeah, because usually you would get weak convergence and convergence of the q's moment. But sometimes we don't have those. Actually, in these cases, we'll always have them, I think, but it makes things a bit easier. So in these cases, say, because I make like fairly strong assumptions here, that could be like a bit weakened in general, because we kind of assume now that everything is actually strongly convex, which of course in machine learning problems it's usually is like not the case, but for now we have this convexity assumption, and we also assume a certain smoothness of the paths. Yeah, so we need like a gradient and a Hessian to exist and to actually be continuous. What we get then for the constant learning rate case is we have that the process has a unique stationary measure. And there are some parameters such that we converge at an exponential speed to the stationary measure. Yeah, and okay, and this sort of depends only on the initial state. Yeah, so this is not too important, but we get an exponential speed, which I think is quite fascinating. Because I mean that's very fast, and we usually, if we think of stochastic gradient descent, we think of very slow convergence. Okay, slow convergence lead to a minimizer rather than a stationary measure, but I was quite surprised in the beginning when I've seen this, and this is pretty much based on previous results that we know about such processes. Yeah, so there's not too much new in here. What is a bit unfortunate is it's quite hard to describe, or probably impossible to describe, the stationary measure pi c. At least I think like case like I think like in a 1D or 2D, I think there's a chance actually, but not a very good chance. So we just know there's like some stable behavior, namely we converge to a stationary measure, but we don't quite know what it is. I will show you some plots right now. Yeah, but this is a very simple test example with like 3 data sets. And we compute all of these ODEs analytically. Yeah, so there should technically be, like, aside from floating point errors, this should be very precise. Yeah, and there we see that, yeah, I mean, first we compare the discrete algorithm with the continuous algorithm, and we see that they actually match very closely. And we also see that if the eta gets smaller, we sort of concentrate around the actual minimizer, which is 0.5 in this case. No, so but what we also see is, and okay, it's a bit hard to see here, they're very, very much non-Gaussian. Yeah, so if you're thinking of like this could be something Gaussian, I mean, okay, these look a bit Gaussian, to be honest. But for instance, we know that they are all living on a complex space. So yeah, all in a complex space from 0 to 2, because these are sort of, I mean, we kind of jump between minimizers here. Yeah, that's between the minimizers of these potentials. And these go from -2 up to +2. Yeah, and we sort of just jump on this, or we just are in this convex set, actually this interval in this case. And that means that like a Gaussian, like saying something, this could be Gaussian for like a finite eta is like very unlikely. It would be quite interesting to see actually whether these measures satisfy certain properties. Yeah, so I mean, say like statistical properties. So what, for instance, what happens if we get more data in such a case? Do we actually concentrate on a true parameter? Things like this, like are these good summary statistics, or maybe do they actually approximate some posterior, which I don't actually think they do. But I think they're very interesting questions regarding these distributions. In a decreasing learning rate case, we can indeed show that the process psi of t converges to the minimizer of the optimization problem, also in this Wasserstein distance and probably in probability, I guess. I can probably show this as well, as t goes to infinity. But unfortunately, we don't have a rate for this result. So the rate gets lost on the way, which interestingly, if you analyze the stochastic differential equation I mentioned in the beginning, for this we also don't have a rate. Okay, so somehow this rate gets lost for both models, which is quite a shame, but yeah, I think we're working on it to try to improve this. This proof actually was much more involved because it contains this very interesting case where you have this rate matrix B of this process J that actually like sort of, yeah, I mean, all the entries go to infinity and the diagonal goes to minus infinity, which is usually something that people exclude when they talk about these PDMPs, or at least in the works that I read, it's usually excluded. So they really want the rate matrix to be bounded. And that is why this was much harder to prove, because there's like much fewer original works on this. But we can show that our stochastic gradient process converges to a point. Okay, and if we now look at, if we now want to know how fast it converges, there's like sort of different answers. And of course, the hope would be that it converges also exponentially, because that would mean that we have a very good optimal rate for stochastic gradient descent. And in some examples, so the top ones are the continuous time stochastic gradient descent algorithms. We sometimes see exponential convergence. We sometimes see very much not good exponential convergence. Yeah, so this is only rational. And it seems to depend on how we choose the learning rates, actually. Yeah, so it could be that if we choose learning rate at an exponential decay, that we also get an exponential decay in the convergence. For a rational decay, we get a rational decay. But yeah, for now we only have plots. Unfortunately, we can't say much more at this state. Okay, so this could be a good moment for like some questions if somebody has some, because then I can sip a bit of tea.
Well, yeah, now that you bring it, this is very nice. I just was wondering the following. I mean, you make an emphasis on the convergence with respect to the time, right? That you introduce this time in the continuous formulation, and you say, okay, I want to show, for instance, some kind of weak convergence and rate with respect to this time.
Yeah.
Still, when you go and implement this, you will have a number of evaluations of gradients that you have to deal with. So the standard question here is how is the rate with respect to the work, right? I mean, for example, if you want to achieve in some probabilistic sense a distance to the optimum, what will be the expected work in terms of the number of gradient evaluations, which is not I mean, it's not at least direct from the continuous time formulation, right?
No, that's a very, very good question. And that actually becomes, and I mean, you're totally right. I mean, if I have this exponential rate here, so in this example, this will get very, very badly as time gets bigger, because I need many, many gradient evaluations then, because I mean, I do very small time steps in the end, or I do very small, so really time steps, or very small steps in between, so the waiting times will be very, very small. So you're absolutely right. This is very, very expensive to do in this setting in practice. So I think what should probably rather been done actually in practice is rather not let learning rate go to 0, but actually rather let the so let's let the batch size go to n. So okay, I've been talking only about like having like one single data set at a time, but of course you could pick more than one, and sort of have like a sum, have like a mean over like m less than n, and optimize with respect to like a couple of ones at a time, and then let this get bigger. This should have the same effect.
So what we did was to use correlation between iterations, right? I mean, I don't know if you saw it, but we have this multi-iteration algorithm that essentially tries to exploit this correlation to reduce the work at the end. But in the strongly convex case, like you have, one still has exponential convergence with respect to the iterations, but then of course you have to do a little bit more work to actually bring it back to the actual computational work in terms of the number of evaluations, right, of the gradients. Then you can get at least at the end we got the complexity in terms of this accuracy of the optimizer. But yeah, one has to work a little bit to translate the iteration speed of convergence to actual work, right?
Yeah, no, absolutely. I kind of ignoring this during this talk all the time.
No, the continuous is very neat, like you said, right? Because there is no complication in the discretization, and you get these very nice results of exponential convergence. Now, on top of that, you have to start, putting the discrete to get the evaluations and finally the complexity. Very nice.
Yeah.
So,
I will come back to that towards the end, and again we can talk about
cool.
again later.
Thank you.
No, thank you so much. So then, okay, this was all this exact setting with discrete data. So I said in the beginning we do also continuous data, and what I mean with continuous data is rather than optimizing over a sum, we optimize over some integral. Yeah, so that's kind of the whole idea. Yeah, we now have here the integral over some compact space S with respect to some probability measure, and okay, we integrate this function f, and f is like sort of well behaved again, and we again assume that this is all well posed or well defined, say. So there is some minimizer theta star, and of course optimization options like this also actually appear in multiple applications. Yeah, you could think of robust optimization, which I'm sure some people here do as well. Then you could think of functional data analysis, where you actually observe a function rather than data set. Like very famous currently physics informed neural networks. We also implemented something like this. In variational inference, you try to often optimize some variance, some evidence lower bound. Where you have an integral of this form. Actually, usually it's non-compact, but in some cases it is compact. And then one example, which I think especially in the inverse problems literature you find a lot, like when doing image reconstruction, is that people actually like to work with integral operators rather than with matrices, because obviously in very high dimensions, sometimes you can get effects that happen more that look more like on a functional level, and therefore this could also be interesting as a model just for something very high dimensional, like a high dimensional image or spatial model or something, where you say, okay, let's try to understand the continuous setting rather than a discrete setting.
Yeah, you can mention also optimal experimental design. That falls into this and is very applied and also very interesting from the theoretical perspective. Expected information gain optimization, for example.
Absolutely. I think then you would probably have like a Fisher information metric in here.
Yeah, you have this cool black label.
Exactly. And exactly. So physics from neural networks would look a bit like this. Where you kind of say, okay, I have my PDE here. It looks a bit like a bit weird now, like very general setting. Some differential operators, some boundary conditions. And then what you do is you replace U not by an FEM basis, but by some neural network, and you try to find parameters for U such that a certain loss is minimized, which would be something like this. And then what people usually do is they sort of just replace integral by a quadrature rule, which I mean, of course you can do, but you can also try to solve it immediately in its integral formulation. Yeah, which I think is more interesting. So how do we solve a problem like this? The answer is again stochastic gradient descent, and I think that's something many people don't actually know. But stochastic gradient descent never was written down for a sum, or I mean, it was written down later. But the original paper actually was solving equations that contain expected values. And what you just do in this particular case is, rather than sampling from the indices, you just sample from pi. Yeah, where pi is this probability measure. And then you can actually show that yeah, you don't actually need to compute this integral ever. You also don't need to approximate it in a classical sense. Yeah, so you don't need any quadrature rule. Yeah, you just need to do essentially Monte Carlo. Yeah, because in the end it's essentially Monte Carlo. And of course, in this case, you think of like an epoch. Of course, it's infinite in general. Although, of course, this could also be. I mean, this can be like a very arbitrary probability measure. Yeah, so the first case is just contained in the second case, where you could say, okay, this is like a discrete measure. But it could also be something with a Lebesgue density. It could be something without Lebesgue density. Yeah, whatever you want. Yeah, it's very general. Just as S should be compact. Okay, so how do we? I mean, what do we do now? So I mean, of course, we could say to do this in continuous time. Yeah, we just define a Markov pure jump process on, say, this now continuous index set. Yeah, S, which is just an interval now from -1 to +1, and we choose this pure Markov jump process such that it converges to the measure pi. And then we're sort of back to the original setting. What is like a bit unfortunate about this, I mean, actually knowing that we have this certain structure can be very helpful, yeah, because we know, okay, it's a certain spatial structure that we can see. And if we just do essentially this, or we just like sample independently from pi, essentially, kind of ignore the spatial structure. And it could be interesting to actually try to go for something that actually uses the spatial structure in one way or another. Then one question is, I mentioned this before, this regularization that you get from not letting eta go to 0, but letting eta being stuck somewhere, and not actually converging to the minimizer, but converging to some area around the minimizer. This, of course, would probably very much depend on how we choose this process I. And then thirdly, this measure pi could actually be quite complicated. Yeah, so you could say you do some bus optimization with respect to a posterior measure from Bayesian inference problem. Yeah, or pi could just be given from some statistical physics simulation. Yeah, so if pi is stationary measure of your Ising model, for instance, that you want to control, yeah, in that case, also like we could not sample independently. Yeah, so this idea wouldn't really work. So the idea was, when we are in the setting where we have continuous data, we also want to allow for more general index processes. And more general includes, for instance, like having a diffusion process, okay, which probably is the most brutal thing you could do, or like almost the most brutal thing you could do. Yeah, where you say you cover your space using this diffusion process. So it's like a reflected diffusion on this -1 to +1 interval. Yeah, and has stationary measure also, so the uniform distribution is stationary measure. And then you couple this diffusion process with your gradient flow. And you get this actually, which I cannot fully explain, but I think it's very nice. You get this actually very nice homogenization for theta of t and this multi-scale process. And yeah, and then we sort of learn, okay, I mean, can we actually get some more information from some spatial structure? Because obviously this is a continuous process, so it clearly uses some spatial feature. Can we actually use, say, some MCMC method or like say, if we are in this setting where we obtain samples from pi through MCMC, can we still use those? Or is it important that our samples are always like pretty much independent? So first we need some assumptions on this index process, and to be sort of similar to the paper, and I'll call this process V. And what's essentially important is that it is a Feller process that has a stationary measure, and it's a stationary Feller process. Actually, it's a stationary Feller process that has a stationary measure, and it's exponentially ergodic. Yeah, so it converges at exponential speeds to its stationary distribution. And distribution, of course, is pi. Yeah, exactly. And examples are, for instance, as I just said, Markov jump processes. So that would be like closer to the original discrete data setting. Yeah, so this is fully contained. But we can also do reflected Levy processes. Yeah, so instead of just a diffusion, you could also have a diffusion plus jumps, or you could have just jumps or just a diffusion. And of course, I mean, okay, this is sort of like 1D now. Of course, like finite products of such processes would work as well. And then we get the constant learning rate case, now again from just coupling our gradient flow with this diffusion process. And here we actually need some more assumptions on this ODE, actually on F. Yeah, so it needs to be fairly smooth in both variables, actually, because I mean, we do something quite weird. Yeah, we have something that is, I mean, we want to couple an ODE to a diffusion process. I mean, nobody's ever allowed us to do that. But with these assumptions, we get that this ODE is actually well defined. So I just mentioned the constant learning rates, and I didn't really mention this epsilon, but there's like some epsilon that we define here, and it's essentially used for rescaling the process. So if the epsilon is like rather big, then this process will move rather slowly. If the epsilon gets smaller, then we kind of like get a very short correlation length, and and a very, very quickly moving process. So, and then we sort of can ask the same questions as before, namely, do we actually approximate this full gradient flow with our process? Yeah, so this minus gradient of this integral of f, and indeed we can show that we do, where we get essentially the same result. It's a bit different because we now have like an additional weight in here, but otherwise it's essentially the same result. Yeah, so we see that our process approximates the full gradient flow. Then the question is, what happens with the decreasing learning rate? Because we have just talked about continuous learning rate for now, and can we somehow let epsilon go to 0 slowly over time to get something like this? So diffusion process, say, it moves very slowly in the beginning and then more faster towards the end, and we actually get this by like rescaling time in the process V. And then coupling it with the gradient flow, and we can then see when we look at the long-term behavior that is actually indeed converges to the correct minimizer. Also here we see that we get essentially the same results as before. We need again some convexity assumptions, but then we can also show in the continuous learning rate, in the constant learning rate case, we can show that we converge to a unique stationary measure at exponential speed in Wasserstein 1 distance. And as I just said, identify the minimizer in the decreasing learning rate setting. And here we sort of use different theory, but also from this paper by Chris and Heyer. Okay, so how does it look in practice? And I think that's maybe the more interesting question for this particular setting. So like for maybe for now. So this is a very simple polynomial, like very simple regression problem where we observe a whole function. So we see some sine function actually plus some Gaussian noise. This Gaussian noise has a certain correlation, but it's very weak. So what we will do actually is we will ignore the correlation and just try to minimize this integral. So it's the integral of this function, of this data function that we can evaluate at any point in y minus like some sum of polynomials. So and these are like not monomials. I mean, I think should be Legendre polynomials. Which sort of makes sense with this integral. and then we add some L2 regularization to make sure that everything is strongly convex. Yeah, what we want to do is, okay, we actually want to see again how it converges, and we want to see how this index process actually influences the solution. So what we do is we use the reflected diffusion I mentioned in the beginning. So it's the same setting actually. We're in the interval -1 to 1. And we also will use a Markov jump process where we essentially wait a certain waiting time, and then we independently jump to another state sample from the uniform measure. And of course also compare this also to discrete stochastic gradient descent. We discuss the gradient flows with an implicit midpoint rule, just because that's more stable. And the index process we use like very trivial Euler-Maruyama discretization with what is trivial is reflection. I mean, it's actually quite hard, I think, to get a good reflection, a good description of reflection numerically, but we just say we do it as easy as possible, although it actually converges quite slowly, therefore, but it doesn't really matter to us now. And of course, we can sample the Markov pure jump process, we can sample it precisely with a certain step size. What we see then is, depending on the setting and depending on how we choose parameters, we sometimes see like literally no convergence. I will show you a table in a second. And we see very fast convergence for other settings. So particularly good actually is it's one setting with a reflected diffusion, and a large diffusion coefficient in front of it. So it's a very fast moving diffusion essentially. And the ones that like don't converge at all or hardly converge are the ones that move very slowly. So this diffusion process like doesn't really move at all, I think. So it's really hard to actually, we will never like sort of, it will take years to cover all the data, I think, which is why this is doing so badly. And this one also is a Markov pure jump process that essentially doesn't really jump, which also leads to bad convergence. And then what's actually interesting is we actually see the best results when we compare our reconstruction to the truth. We see the best results actually for the stochastic gradient process with the diffusion process, which is something I didn't expect. But these are the best results. And if we just do stochastic gradient descent, or we combine stochastic gradient descent with the midpoint rule, then we're doing not quite as well. And the Markov pure jump process actually does the worst overall, which I also wouldn't have guessed actually.
So again, just to clarify, right? I mean, so you're showing here error versus different choices of parameters and algorithms, right? How do we see the effort that was put on each of these results that we see here?
So the effort was exactly identical for all of them. The only difference is, okay, so it was a bit higher for this one because we needed to also compute this diffusion process, but that's very fast. So I didn't really count this, I think. So, but the effort in terms of gradient evaluations is identical in each of the algorithms.
Thank you.
Okay, and so what we've seen actually at looking at the plots is we get quite quickly to equilibrium if we're not in very slowly moving settings. And actually the implicit regularization, which is probably what actually determines these different errors, has an influence. So it has an influence which kind of process we use for choosing the index, which I think is very interesting. And as I said, computation cost is actually fairly equivalent, which means gradient evaluations are exactly identical for all of the examples. Okay, there's like some take-home messages. So we introduced the continuous time model for stochastic gradient descent with either discrete or continuous data. We're able to capture most properties of stochastic gradient descent while sticking to a continuous time setting, which makes especially analysis much easier, or easier, say. The subsampling can be more or less independent, which is kind of the first part of the talk, where we just really sort of sample independently from the indices, or follow a more general filler process. And then in the constant learning rate case, we have a unique stationary measure to which we converge at exponential speed. In the increasing learning rate case, we actually converge to the minimizer of the problem, of the optimization problem, although we don't know at which speed that is. Some other related work, or where do we go from here? And obviously the question is, can we actually get exponential convergence in the decreasing learning rate case? That would be very interesting to know. Then, and that's it's like what Raoul mentioned before, is how do we actually get an efficient practical algorithm from this? Because that's not clear whatsoever. Actually, it's in general, I've not seen much works on actually discretizing these piecewise deterministic Markov processes, which I think is in general a very interesting problem actually, and try to retain things like a stationary distribution, or try to get close to a correct stationary distribution. So in this talk, I talked only about strongly convex and smooth optimization. In this preprint that I submitted a couple of weeks ago, I also look at certain L1 regularization, which makes the things non-smooth, and also at like randomized Ln-Kan, which makes the things, in this case, non-smooth and non-convex, although only like a bit non-convex. So it's not a neural network, but I think nonetheless very, very interesting. It especially makes the work with the gradient flows much more interesting because they're now subgradient flows, and actually, so it's like set valued. So set value dynamical systems. Which makes things a bit more technical, but very fun to work with.
But I mean, just one